These are your 8-8 factoring notes. We're still continuing with factoring. We're going to look at, in the next two sections, a couple special case types of factoring. So we have taken a greatest common factor. You can take a greatest common factor out of any type of polynomial. We factored by grouping when you have an even amount of terms. And then we worked with trinomials. So now we're going to talk about a couple other instances of what can occur and how to factor when it occurs, what type of multiplication occurs. So the first of the two special types is what we call difference of perfect squares. So a difference of perfect squares is just that. If you listen to the words and you understand what a difference means in math and what a perfect square means in math, you should understand what they are. It's when you have it's the product. So after you multiplied two binomials, and the outer and inner terms didn't combine to make a trinomial, they actually cancel out. And so you're only left with two terms. Okay, so let me give you an example of this. If I had x plus 3 times the quantity x minus 3, when I FOIL that, first terms gives me x squared, outer terms gives me negative 3x, inner terms gives me a positive 3x, and the last terms makes negative 9. So usually what we would do at this point, we would combine the outer and the inner, but in this case, when you combine them, a positive 3x and a negative 3x cancel, and so what you're left with is an x squared minus 9. So what you're left with is a difference, there's the difference, subtraction, of perfect squares. Now I'm going to get into that definition in just a second, but this is a perfect square, and 9 is a perfect square. So how do you know a number is a perfect square or not, and how do you know a variable is a perfect square? I'm going to explain on the next slide. So how you factor these, you have a couple different options. You're going to pick up on a really easy pattern very quickly. So again, we always look for greatest common factor first if you can, okay, and you factor that out, and we never leave that off. If you factor out a GCF, that just becomes part of the answer. You can use guess, check, and revise again. You can use your square method again, and you can use your product and sums table. I will tell you, when you do the product and sums table, a nice clue that you'll have a difference of perfect squares, you actually could rewrite each of these difference of perfect squares as a trinomial. And so what you're really looking for is what multiplies to give you negative 9 and what adds up to 0. Because there is no x term, there is no middle term, there's no b value in the middle, or your b value is 0. So one of the options is to make that middle term go away. You're looking for what would multiply to give me negative 9, but adds to give me 0. And what you're going to find is that you're always, in order to get a negative product, you're going to have a positive and a negative. And in order to get it to equal 0, they're going to be opposite of the same number, 3 and negative 3, or 5 and negative 5. You always look for more factoring. So because this type of factoring is so simple, they're going to beef it up by making you, they're going to complicate it by making you take a GCF out or factor again. So always look for more factoring. Let's talk about perfect squares. I have this nice table of values here, and n represents all the first 20 digits. Okay, and then n squared represents the first 20 squares. And so 1 squared is 1 times 1, and that's actually 1. 2 squared would be 2 times 2, which is 4. 3 squared is 9, on down the line. So I'm just going to reveal all of these perfect squares for you. You can pause it, and you can write them down. Many of these will be pretty familiar to you. When you get up into the 12 on up, or 13 to 20, they may not be as familiar. But the first 10, the first 12 of these should be familiar. So what you have to do is you have to sort of put these special numbers, they're special numbers, in a spot in your brain that lets an alarm off saying, wait a second, that's one of those special perfect squares. So those are perfect squares of numbers. So you'll be looking for that as the second term or maybe the first term, just depending. So how do you know if a variable is a perfect square? A variable is perfect if its exponent is divisible by 2. If you think about it, squared means to multiply by 2. So x times x is a perfect square of x. You multiplied x by itself to get x squared. If I multiply x to the third times x to the third, x to the sixth is a perfect square of x to the third. Okay, I multiplied x to the third by itself. X to the fourth times x to the fourth gives me x to the eighth. And so all of these represent perfect squares. The exponent of each of these is divisible by 2. And how you undo it, how you take the square root, that should say the square root of a variable, to undo, I'm sorry, no, that's right. I read it wrong, sorry. To undo the square of a variable, that really means to take the square root. So when you undo the square of a variable, you're really taking the square root of it. You divide that variable by 2. If I gave you x to the 6th, we're asking what power of x did you multiply by itself to get x to the 6th? If you divide the 6 by 2, you realize that it's x to the 3rd times x to the 3rd. If I gave you x to the 24th, that is perfect because 24 is even. And not only is it perfect, it's perfect of x to the 12th, because x to the 12th times x to the 12th would give you x to the 24th. We learned in chapter 7, or I believe in the chapter 8, I can't remember what chapter it was now, that when you multiply these things, we add the exponents. So if you just simply divide that by 2, it's like taking the square root of it. To take the square root of any of the squares in this list, for instance, if you want to figure out what the square root of 81 is, you can look at this list, and that means it's this perfect square of 9. You can also just take the square root of 81 and know that it's 9. So that'll get you back to that base number that you squared. So let's go ahead and try these. So I look at number 1. Is there a GCF? There is not. So using guess and check, I'm going to see what will multiply to give me m squared. Well, I know an m and an m will make m squared. And then I'm looking for two numbers that multiply to give me negative 64. But you also notice they don't add up to anything, so they add up to 0m. So if you want to, you can always rewrite it this way if necessary. Make it a trinomial. Use what we've already talked about. And so to get a product that's a negative, I got to have one positive and one negative value. And to get 64, I need to multiply the same number together, just opposite signs, so that it subtracts to 0 or adds to 0. So I'm going to put a positive 8 in there and a negative 8 in there. And the middle terms would be a positive 8m and a negative 8m. I'm good to go. So I did a quick check. It works out. That's my solution. Number 2, I'm looking for a GCF between 16 and 81. I don't see one. Y's and Z's don't have anything in common. But what I do notice is that 16 is a perfect square of 4. 81 is a perfect square of 9. And y squared and z squared are both perfect because they're both even. So I'm going to use guess, check, and revise again. And how would I get a 16y squared? Multiplying by itself, squaring a number. I'd have to have a 4y here and a 4y here. How do I make 81z squared and also get 0? It'd be a positive 9z and a negative 9z. So I showed both of those using just guess and check. When you get into number 3 here, let's do a product sum table. So if you're going to do a product sum table, they only work with trinomials. So I'm going to rewrite it as a trinomial. What multiplies to give me negative 49 and what adds to give me 0. So to get a product of negative 49, I got to have one positive and one negative. This would already be in your product sum chart. And then adds to give me 0, you're going to have a 7 and a negative 7. So you can go ahead and show the work if you like that work. First term, x squared, plus 7x minus 7x minus 49. You break it into 4 equal parts, split it down the middle, take out an x, you're left with x plus 7, take out a negative 7, and you're left with x plus 7. That tells me I'm doing it right. And so you end up with x minus 7 times x plus 7. And again, if you like guess and check better, then use guess and check. Let me go up here real quick and I'll show you with your squares how to do number 1, just to give you another example. So for those of you that like the Punnett squares, we do the same thing as before. We put our first term in here, m squared. We put our last term in the bottom right, negative 64. And this diagonal has to equal 0m. So if you're going to use the square method, you kind of have to have a trinomial to use it with. So to get an m squared, I would guess m and m. To get negative 64, I would guess negative 8 and positive 8. And that gives me an 8m and a negative 8m. And that does, in fact, check out. And so m plus 8, m minus 8. If you look at number 4, there is no GCF, okay? And I look at that, and it is not a difference of perfect squares. It's actually a sum of perfect squares. So I'm going to use my sum and difference chart real quick, one more time. And I look at this, and I set up my product sum table. And I look for what 2 numbers that multiply to give me a positive 25 and adds to give me 0. If you go to your list of 25s, you will not find 0 in that list. Just to show you, in your product sums, the only numbers that multiply to give you a positive 25 are 1 and 25, negative 1 and negative 25, positive 5 and positive 5, or negative 5 and negative 5, all of which do not add up to 0. This will give us a sum of 26, negative 26, 10, and negative 10. So I've exhausted all possibilities. This is prime. This does not exist. Now, for people that use the product sum table, it's going to be easy to see that. Those of you that use guess, check, and revise, you better be careful that you actually check and revise. Most common answer, I'll just show you, is x plus 5, x minus 5. That is the most common guess because you see the 2 terms, you see that they're perfect, and you try to make it work. This will give you x squared minus 25, not plus 25. Another common mistake is people will say x plus 5 times x plus 5. When you have the same signs and the same terms, the middle terms will not cancel. You have to have one positive and one negative to make 0 in the middle. First gives you x squared, outer gives you 5x, inner gives you positive 5x, and last gives you 25. So even though you get the positive 25 this time, you also have a middle term of 10x. The same thing would hold true if you did x minus 5 times x minus 5. You'll have a negative 10x in the middle. So this is prime. We've exhausted all possibilities. There's a reason we call it a difference of perfect squares, not a sum of perfect squares. So be careful with those type of problems. Just a couple more. Oh, those aren't supposed to be in there. Sorry, I thought I erased those. And I thought I erased those. I guess that's where we're going to stop. I thought I had some more on your actual notes. Let me see what I have on your notes. Is that where I stopped? All right. So we're going to look for, no, these must be the wrong notes. I apologize. They did not save. You can see it on your notes. It asks you, how do you know if a variable is a perfect square? And then I want you to factor. So I'll just replace that. I want you to factor x to the 4th minus 16. It must not have saved since I made those changes. I apologize. And that is your notes. Good luck.